Good morning, everyone. Thank you again for coming back.
Here.
So, what I'd like to discuss today is the analysis of local stability and global characterization of the global dynamics of heavy-tailed stochastic gradient descent, especially when gradient weighting is involved. So, let me quickly recap what I discussed toward the end of Monday's lecture. So, basically, what this picture shows is what I would like to explain today. Why this is the case, how you prove this, how you investigate this kind of behaviors. So again, this is the length, those lengths here, and here there are sharp and wide or flat local minima, and these are light tail dynamics. The histogram of the locations visited by SGD light tail dynamics. This is the histogram of the locations visited by heavy tail SGD. These ones are pure version of SGD, and these ones are clipped versions. So in the light tail case, there's no difference. They have just no ability to escape where the attraction field that has started with. On the other hand, in heavy tail cases, both clipped pure version and the clipped version explore all four local minima. So they are capable of exploration, but the pure version still visits sharp local minima. But the clipped version, the sharp local minima is almost completely eliminated from its trajectory. So this can be very rigorously understood with what I'm going to, the mathematical framework that I'm going to introduce today. And but the final statement is so this is where I want to get at. So the stochastic gradient descent with scale time converges to a Markov chain. In particular, Markov jump process. So continuous time, discrete state space Markov chain. And the discrete state space consists of the local minima, in particular, only wide or flat local minima. So the sharp local minima disappears from the limit process, and because of that, you get this theorem. So this is you're counting the amount of time that you are in around sharp local minima, and this is the whole the entire amount of time. So the fraction, this is a fraction of time that you spend around sharp local minima, and that goes to 0. So among the total amount of time, the total training horizons, the amount of time that you spend around sharp local minima, it becomes negligible. Again, what this means is that if you arbitrarily stop training, you don't have to monitor anything, but you just run long enough time and stop at an arbitrary time, you're almost guaranteed to be around flat local minima. You're guaranteed to be not to be around sharp. Okay, so So let's see what are the mathematical machineries that allow to prove this test. Yes.
Just a question. Is it due, I mean, is average time tends to zero? Is it due to you almost never go to some local minima, or it is so easy to get out?
Yeah, that's exactly right. So
The second or the first?
right. So so if it so first if it's heavy tail, then it's easy to get out of any that's the pure version of this movie. And but if you do clipping, what happens is that with the right clipping threshold, sharp local minima is still easy to escape. But flat wide local minima, it takes more than one step to.
Yes, okay, but is it more of, I mean, can we say that it is harder to get there? I mean, it is harder to get into
No, it's
local
not
minima.
it's not harder to get to fall in the sharp local minima. So it's they're same more or less the same chance. But I mean it's slightly different, but it's not significantly different. What's significant difference is that once you are in wide local minima, then you're trapped. So in a bad place, whether it is clipped or not, as far as it's heavy tail, you can escape easily from bad places. But once you're in good place, without clipping, you still get out of there easily. But with clipping, you are trapped.
So can I really say as for frequency of times you visit sharp minimum is the same as a visiting frequency of times you visit
So
wide
it's not the
minimum,
same.
but the time frequency of time you are spending there, they're different.
So they both go to zero because once you're trapped in wide local minima, you can barely get out of there. So the amount of time you spend in the wide local minima, you're trapped in the wide local minima dominates the whole time horizon. So you don't get it often, but whenever you jump out of whenever you move to some local minimum, there's not a significant difference. So
I'm going to define what a sharp and what a wide local minimum is, because I have a feeling it's a circular definition in the narrative up to now.
So yes, it really defines this. Any other questions? All right. Okay. So all right. Maybe I can define start with defining that as actually maybe that so at a local minimum, there's a shortest distance to the outside of the attractive. So in this case, this is the shortest distance. So that we call that R. And C is the clipping threshold. You divide by R by C and then take the ceiling. That's the required number of jumps to get out of this. So this number L will be different. For example, here it will be 1. Here it may be 3. So this is not exactly the width, but discretized width. And when this discretized width is different, then there's asymptotic difference. The rate of the scale of the exit time changes.
So, like in my own words, local minimum is sharp if it is not wide, and a wide local minimum is one with sufficiently big R.
That's right. That's right. So here, in this theorem, sharp minima is actually everything that's not widest. Except for the widest, I'm considering everything else sharp. Only the widest ones. Sorry. All right. Thanks. Okay, so let me start. All right. So here's the object that we want to study. So W. So this what we actually have is for general dynamical systems, not just SGD. So I'm using A here and just whatever sigma is. But throughout this course, throughout this session, let's assume that we are focusing on stochastic gradients. So you start from X, and we denote the starting point with parentheses. So X W A dot means A dot of X means that it's SGD started from X. So after J plus first step, so this is where you're currently at J step. You move to the direction of A, but only this much. And there's some noise, IID noise, which is also scaled by eta. So in this session, A will always be negative of the gradient of the loss function. So you're moving to the opposite direction of the gradient by eta. So here eta is exactly the learning rate, and A is the potential. So the derivative of the potential, negative. Yeah. So later we're going to state sample type large deviation. So it'll be convenient to have some symbol that refers to the whole trajectory. So this is scaled trajectory of the stochastic gradient descent. And the scaling is by eta. So we are only scaling the time by eta, or 1 over eta. And we denote the, again, here we are denoting the dependence on eta as superscript. Okay, so this is the pure version of SGD if A is negative of F prime. This is the truncated version. So exactly the same. The only difference is I color coded with red color. So this means truncated at B. So the only difference is that instead of making this much step, we take the truncation operator there. So what's phi B? Phi B is the same direction, but if the magnitude of X is too large, larger than B, then you cut it at B. You clip it at B. Okay, so it's truncation right there. And we're also going to call the whole path of this process as with boldface bold font W. Okay, and we're going to make assumptions, and these are usual assumptions. So A1 is heavy tail assumption. So basically, the magnitude of the noise is regularly varying with index alpha. And we also assume that Z has mean 0, of course, because otherwise it's not going to be unbiased stochastic gradient descent. And this is Lipschitz condition for both drift and diffusion coefficient. And the only assumption that we make about sigma is that it's not 0.
W is itself, is it one or multidimensional?
Oh, so here it's one dimensional. But then the exit time analysis generalizes to the multiple dimension. The convergence to the Markov chain is a little bit it's trickier, so it's not as easy to generalize. But the reason we get this convergence to this particular Markov chain is exactly because of the exit time result, and you're going to see that. So so please bear with me. All right. So yeah, that's the setup. Those are the mathematical objects that we are going to study. Now, what we're going to assume, of course, is that so at this point, this is what we made. So okay, so I used F here, but here I'm using U instead. So let me make it F. So F is has the minimum at 0, and what this condition means is that on the left side, the drift, the gradient is to the pushes you to the right. On the right side, it pushes you to the left. What that means is that that's on all the points in I except for 0. What this means is that within I, you are pushed to the local minimum. So this is legitimate attraction field associated with this minimum. Here we are assuming that the minimum is at 0, just without loss of generality. All right. So again, this is just very natural assumption. So here, what I've written here means that if you drive the ODE here as well, using the opposite direction of the derivative, then ODE will converge to the local minimum. So basically, gradient flow will converge to the local minimum 0. All right. So the object of our interest are the exit times. So tau eta is the exit time of W eta, the pure version of SGD. Tau eta clipped at B is the exit time of W eta B. So gradient SGD with gradient. And here I'm introducing some measure that I'm not specifying right now, but this is also the one associated with the clipped SGD. This is one associated with unclipped pure version of SGD. And again, R will be the radius. So I here, I is from negative of SL to SR. So the minimum between these two is the shortest distance to the boundary of the
Sorry.
and J star is exactly the quantity that I defined as so radius divided by the translation threshold. So this is you can think of this as the minimal number of times required to escape from this solution. Okay.
So you assume, like for the heavy tail, you only said something about the absolute value, but you assume that both the left tail and the right tail is non-trivial.
Yeah, you're right. So I'm being a little bit lazy here. So what we actually assume is that both tails have the same index, and so yeah, that's what we assume. All right. So
IID two signed random variables with both tails of the same alpha. Yeah.
sorry.
You have ZI,
Right.
which are IID and signed random variables,
Right.
and both tails are of the same belong to R alpha for the same alpha.
Right, same regular variation index, doesn't have to be same tail, but same regular variation.
Alpha and beta alpha may be different on the left, on the right.
No, same.
Same.
You're assuming same. It's just in this. So in the end, especially in multiple dimensions, you're not using the same. You'll have more different indices for different directions. So okay. So this is the main theorem. The key theorem that leads to this sample path convergence and exit convergence. So let's parse this. It's a little bit complicated, but this is just some scaling. So this is regularly varying. This is 1 over eta. So if this is regularly varying with index negative alpha, then this will be 1 minus alpha. And you take j power, and this is another scaling, like extra scaling. So this whole thing is the scaling. This is the exit time. And here it's a fixed number t. And what is this? So remember that tau was the exit time. And
Excuse me, please.
W,
Would you repeat? Capital I isn't a fixed interval.
right, yeah. Capital I is a fixed.
And then exponential to the minus t comes from the Markovian property, right?
You mean
Yeah.
comes from
From the Stone Markovian property, right?
so
Stone Markovian property.
right. Basically, yes, yeah. So yeah, so I will explain why how this arises. Hopefully it will be clear in half an hour.
So I epsilon is the basin of attraction.
Oh, I epsilon is the covering. So we have class of coverings. So as epsilon becomes smaller, I epsilon becomes close to I. So you can think of I if I, then this may be I epsilon with epsilon mute. So
But what is I? Sorry, I'm not aware.
oh, I is just whatever interval that we
But that's the related to the basin.
right. So I is the attraction field because what we assume is that on I, except for 0, you have drift, positive drift on the left side and negative drift on the right side.
I epsilon is bigger than I. So I'm surprised that you are allowed to take a bigger set.
Oh, so
Shouldn't it be a smaller, like a shrinking?
oh yes, you're right. I'm sorry. Like yeah, I epsilon should be shrink.
Yeah, otherwise it's,
sorry about that.
You fall on the other side.
So this is I epsilon. Yes. Right. Okay. All right. So how is the exit time? So W at tau is the exit location. The moment that it escapes from the attraction field I, where does it land? So this is exit time. This is exit location. So the joint distribution of the exit time and location follows a measure associated with the location and exponential distribution. So what this means, roughly, like if you ignore this, the supremum over these things, then what this means is that the exit time will be roughly, scaled X time will be roughly exponential distribution, and the exit location will follow this measure, will be distributed according to this measure. Okay, so here, C star is the measure that I didn't exactly define in the previous page, evaluated at I complement, so outside of the. So remember that this defines the distribution of the exit location. Of course, exit location has to be outside of I. So basically, this is a whole mass of this thing, and this is the portion intersects with distribution.
Can I ask a question? So is it true that actually the key thing in the statements is not so much even the limit, but rather the scaling? So what the tau is scaled by, right?
Right. So what this tells you is that how tau scales. Yeah, and also where it lands on as well.
Right, but this is one thing. The limiting distribution is one thing. But sort of what if I'm thinking, what's the difference between the tails are lighter or heavier? Right, sort of it actually appears in the scaling, right, not in the limit.
Oh, what you mean in the limit here?
Right, so it doesn't appear there. It appears in the scaling. It comes from the left hand side.
So
The limit distribution is exponential. It's just that the scaling is.
But the scaling is different. If you have a small eta, right? Then we have a big difference in the scaling, right?
yeah, exactly. So if it's light tail, the scaling will be far longer. So it's
Right.
going to be like exponential. But
Right.
here it's polynomial. So that's a big difference between light and heavy tails.
Right.
But also, right. So I hope I will make this clear later. But we have very precise characterization of this location measure, and this is coming from the exact asymptotics of the heavy-tailed large dimensions. So if you have low asymptotics, no, you cannot do this. So yeah. All right. Any other question? So there is a yeah. So
Just one more question.
sure.
Does it depend on the original function f or not?
Sorry.
Does it depend on the original function f or not?
So it this appears in this
Only there.
yeah.
So for example, if f is linear or quadratic, it doesn't
Right.
matter.
Well, so if you have some yeah, so you may be able to come up with I think there's some regularity condition, like I don't exactly remember what was the
The
precise.
only condition was its derivative is at least c over x.
Sorry,
Its derivative is c over x at least. If prime times x is
yeah, right. So this is one condition, right? Maybe Xing will remember. So what was the smoothness condition that we needed?
I think we just assume that f is C1 and with
C1.
that condition.
Okay. So we very weak condition, very. So typical I think previous literature assumes like 3 times differentiability.
That's not about differentiability. That's I just wonder, does it depend on how quickly it goes to
Oh,
zero? I mean, say x to some power or log x or something
also
like that.
yes for that matter we assume the leachage condition, so it cannot grow faster than linear.
So no, not cube. Cube should be still. Is it around zero or everywhere? Doesn't matter. If you assume this condition.
So here we only consider I like
Yes, and then
okay.
x cubed is still okay, right? X
Right,
cubed
so
still
that's-
okay.
So in principle, because it's compact, you can consider pretty much anything.
Yeah, okay, so the only functions which are not good, not so good are something like x to power less than 1, right? Or still okay? Oh no, still okay. Which functions are excluded by this
So-
condition?
Something like this will be excluded.
Which is root x. Root x. Root x.
Yes, right.
So x to some power less than 1.
That's right. So at around 0.
Starting from linear functions.
So linear function is okay, but sharp.
Okay, okay, great. Makes sense, okay.
Any other question? All right. Okay, so okay, so this is the main theorem for clipped SGD. Almost exactly the same theorem holds for pure SGD, but the difference is that there's no power here. So remember that here it was J, and here it's no power. And the measure is a bit different. So there are different measures. So you see that regardless of the width, if it's a pure version of SGD, the exit time scale is in the same. But here, the width of the attraction field, the discretized width of the attraction field, defines the rate at which the scaling parameter increases. So the exit time scales at a different rate depending on the width. If it's scaled, if it's clipped SGD, and if it's pure version of SGD, regardless of the width, it has the same scaling of the exit time. So whether it's sharp or flat, it takes pretty much the same amount of time. Although, of course, when you land on one of those attraction fields, you're more likely to land on wide ones. So because of that, you still have some preference of wide local minima over sharp local minima, even if you have unflipped SGD, heavy-tailed SGD. However, that's total mass. So if you have many sharp local minima, so that the total mass of this sharp local minima dominates the whole space. You have only one, let's say, wide minima that is wider than sharps, but other sharp ones, but still, if you consider the whole space is a small part of it, then you're not going to be visiting that more than the entirety of the other ones. On the other hand, in flip case, even that case, this wide one will dominate everything else. Okay.
Can I ask another question? So it looks like sort of this calls for clipping as much as possible, right? You want to clip more, is it correct?
So if you clip too often, like if you make the clipping size too small, then everything will be wide local minima. So even sharp local minima will have large index here. This one will be is just a ratio between radius and d. So if d is very small, then even small r will lead to large j. So it'll be very difficult to escape from sharp one. So basically, it becomes a light tail dynamics.
But it will be much more difficult to escape. So right.
Wider one, yes, but now it becomes very similar to light tail one. So in the light tail case, once you are in, whether it's wide or sharp, once you're in there, there's basically no way to escape. Like you have to be there until the end of the universe. So And if the clipping size is small, pretty much the same thing. It's not going to be exponential, but eta to the 1 over eta to the 100 is not that much different from e to the 1 over eta. All right. Any other comment, question? Yeah. So
So this is essentially, it's in particular, you get asymptotic independence of location and time.
exactly. Yes. Yes. Right. So that's yeah. So I'm gonna get back to that and that's actually why you get this sample convergence. Okay. Very good. All right. So we have these theorems. So how do we get this? So here's the framework that we found useful. So atom is what it's a notion in Markov chain theory that has been found to be very useful when you're analyzing, for example, a steady state distribution and so forth. Yeah, Pima.
Lower and upper bounds, do they coincide for good sets or not?
Sorry.
Lower and upper bounds, do they coincide for good sets or for good B?
Yeah, on the
You-
previous slide, you had a limb inf and a limb sub. And
Right.
Dima wonders if B is not too crazy. Are they the same?
Oh, good B. Okay. Yeah. So right. So yes, that's what we expect. In fact, for most B's, this will not coincide.
So for most B's, for say for intervals, the same asymptotical behavior. If B is an interval.
Right. So yes. Right. So yeah, that's right. Okay. So yeah. So atom is a part of the state space where your Markov chain visits over and over again. And once your Markov chain is there, the behavior from then on is the same. So that's the actual atom. And we wanted to, so if you think about how these SGD behave, so it will first follow the gradient flow and then linger around the local minimum. But from time to time, it's going to be pushed out of the local minimum because of the stochasticity. But then it will come back. So basically, most of the times, it's going to be around 0. And if you divide the times into same intervals, same length of interval, then at the end of this time interval, either you have escaped or not. If you have escaped, then that's good. If you have not, what is because it's following the gradient flow, you're likely to be around 0. So 0 will play some similar role as atom during our Markov chain theory. Of course, it's not exactly atom because if you pick this to be a singleton 0, then it's not going to be visited infinitely many times. If you make it larger, then the behavior afterward is not going to be the same. So, but then, however, in terms of the asymptotics, large deviation system asymptotic, and that's necessary for the exit time analysis. Around 0, the behavior will be similar enough, and you're going to be visiting this small interval around 0 often enough. So that's the intuitive interpretation of this asymptotic atom. And so we say that a Markov chain possesses an asymptotic atom associated with I So I is the original attraction field. I epsilon is the covering of I. So as I decreases, its epsilon decreases. I epsilon becomes larger and larger, closer to I. So if you take all the unions, then this will cover, eventually cover I. And so, and you can just think of it as in epsilon theory. So just I, so the right point minus I, left point plus I, plus epsilon. C is just a measure, and gamma is a scaling function. So asymptotic atom, again, this is a set, nested set. In particular, this is decreasing set this time. So I is the increasing set, A is a decreasing set, and eventually A is going to be decreasing to a single point 0 in our context. It doesn't have to be in general. But yeah, so, and I here will be something that's eventually covering the attraction field. So for given B, if we can find delta epsilon t such that for any epsilon t that's greater than, so t greater than the tb and epsilon less than epsilon b, this holds. So there are 4 inequalities or 4 limits asymptotics, and delta here is something that goes to 0. You first send t to infinity and epsilon to 0. So roughly speaking, if you ignore infimums and supremum and everything, then you see that there are measures in the upper and lower bound, and there's scaling, there's lim-sup, and probability of interest. And what is this probability of interest? So here, I'll probably to zoom in because of sub and superscripts, layers of sub and superscripts. So so this is the usual notation. How eta, so eta is a dependence of, so we are considering general Markov chain V that's also indexed by eta, parameterized by eta. So you can think of V as a so W as a example of V. And tau here is the first hitting time of this. So what is this? This is first exit time of I epsilon. So something slightly smaller than I. So it's almost exit time of I. And this is again, this is the same thing, exit location. So V at the exit time. Okay. So what this condition describes is if you move this to this side, so let me just do it now. So you can make this. If you look at this, this is a time, exit time of the scaled process, right? And this is exit location. So if the scaled process satisfies large deviations, this is exactly the set that can be described by a process belonging to a set in the past. So this is a event that the process scale process escapes I before time t, and this is the event that it escapes and lands on a particular set t.
Sorry, the scaling is different than in the theorem here.
Right, so this is not the same, so we're gonna find gamma here that matches what we have in that large deviation. So I even stated large deviation. All right, so so basically these two, if you ignore this is more or less an error term, and ignore infimum and supremum, then this is basically what LDP, large deviations for a scaled process would dictate. What is this? So again, this is a heating time of the complement of this set. So what is this set? This is the attraction field minus M. So slightly smaller than an attraction field, and there's atom inside of it. So if this is attraction field and this is I epsilon, then there's A epsilon around 0. This is the amount of time your process is in this region. So it doesn't enter the atom, and it doesn't escape from the attraction. So what this condition dictates is that should be very rare. Rarer than these exit events. Now, if you look at this, A epsilon is atom. So no matter where you start, as far as you are within the attraction field, then within this much time, you should visit the atom. So this is basically the same condition, the condition that corresponds to infinitely visiting the set infinitely often in the Markov chain theory. So you visit atom often. That should be the normal scenario. You cannot stay in the attraction field, within the attraction field, without either hitting atom or escaping it. And this is again the large deviations. So all of these can be established by large deviation. All of these come from large deviation. Problem here though is that we need these infimum and supremum. So this is different from our large deviation formulation. Okay. So okay, so the implication, so once you have asymptotic atoms, then you can actually prove that this upper and lower bounds for scaled exit time and exit rotation. So this is exactly the same form as the main theorem that I started with here. So here, some scaling, exit time, exit location. Scaling, exit time, exit location. So exactly the same form. Just the previous one is a particular example, special case for V being the SGD. All right. So to get the so how do we get this supremum or like uniform version of large deviations? So first, let's first so yesterday I gave you precise statement of the large deviations for Levy processes and random walk. So those are the statements are relatively simple, and they are described in terms of the number of jumps that you have to add to the step functions. The more so this. So if you look at this, so here, if we pick a to be 0 and sigma to be equal to, let's say, 1, then this goes back to the random walk. And there we have the SDE version of this, and that goes back to the Levy process. So Levy driven SDE, of course. So the point here is that what I discussed yesterday is a special case of this, and because this is more general, it requires a little bit more involved formulations. So h is a function that we need to define to state the large deviations, and it's a function that maps initial point, jump sizes, and jump times to a path. What kind of path? This path starts from the starting point x. It follows the gradient flow. So here again, f will be negative of f prime. And almost everywhere it follows the gradient flow, but at the jump times, it makes this much jump. Okay. So you can think of this as a gradient flow perturbed by jumps, just like adding jumps to the step functions. So yeah, so this is exactly what I mean by H. So it follow it H it follows the gradient flow. You add jump here, and then from the point it lands, you follow the gradient flow again. So solution of determinist ODE, and continue in that way. So that's H associated with this size of jumps and these jump times. Is it clear? Okay, that's H. So that's a mapping from this Euclidean space to a path. And D of K, parenthesis A. So again, what's in the parenthesis refers to the starting points. So it's the image of the starting points in A and all possible jump sizes, all possible jump times. So basically, this is what's covered by the starting points A. All the possible paths that can be obtained by starting from A with whatever jump size and jump times. And D less than K is just union of D J's. So basically all the paths that can be obtained with J jumps. So 1, 2, 3 up to k minus 1 jumps. By the way, here there's nothing, no constraint about having 0 here. So this actually dk includes dk minus 1 and so forth. So this is actually not really necessary. In fact, d less than k is equal to dk minus 1 a. But I just wanted to make this consistent with what I have shown last time. So anyway, this is the jump paths that can be obtained from k less than k jumps. And the scaling parameter here is this thing that is probably now familiar, because this is more or less the same scaling parameter as yesterday. All right, so C here again looks similar to what we have seen yesterday. So basically, the measure the distribution of the paths that you can obtain from power law jump sizes, nu alpha also measure in this form, and uniform. Okay, so here this is actually k tuple of uniform distribution. So here Lebesgue measure between 0 and k. So very similar form, but then last time it was function. So the jump sizes and jump times are decided. Then it will be step functions at specific jump times and jump sizes. Here it's still piecewise deterministic processes, but at the deterministic part is not flat. It's a solution of ODE. So that's the measure C. And then this version of gradient large deviations for SGD. So here we have infimum, supremum. I mean infimum and supremum here. And so when A is something that reduces to 0, then supremum over this, you can expect that this will converge to something, some particular number. So the delta that we had in the definition of asymptotic atom will be the error between this one and the limit. All right. So how do we get this? So last time, the way we have obtained this was through the M convergence, right? But can you get this from the same M convergence? So the answer is that we had to make some modifications to the notion of M convergence. But before that, exactly the same thing. So same H as the piecewise deterministic law with perturbations, and these are paths that can be obtained by those k jumps, but with the jump size limited by b. And the same thing, and then same scaling parameter. You get, and the C is also defined. The only difference is that H is replaced with HB, so it's the clipped version of it. And what you get in the end is exactly the same LDP, but here this is different. And the process is split process. So yeah, so there's just a clipped and unclipped version of large deviations for both SGD and clipped SGD, and both of these are directly, almost directly from the M convergence, the uniform version of M convergence. So what do I mean by uniform M convergence? So let me quickly review what M convergence is. So again, M convergence was formulated in this paper by Linskog and Resnick in 2014, published in Probability Survey. And the definition is you have a complete separable metric space. C is a closed set in there. And M is a space of measures, and Borel measures in particular, such that it has a finite mass on S minus C, but you make it slightly smaller. So you increase C a little bit and subtract from S. So it's S minus C, slightly reduced. So as far as you are away from C, you have finite measure. So all of those measures form this space. And the precise definition of the M convergence, so in other words, convergence in this space is in terms of the topology defined by in a very similar way as you topologize the weak convergence. So C is a space of bounded real valued non-negative functions. In particular, the ones that are supported on the portion that's bounded away from C. Okay. Again, let me draw the picture again. I drew this yesterday, but if this is let's say, suppose that this is S, and there's C here, and this is going to be R fattening of C, so the distance is R, so the dotted line will be C, R, and therefore this portion will be S minus C R. Okay. So as R grows, this thing will be smaller. But so this is set of all functions that has some R, for some R supported in this. So it's 0. All right, so the convergence, M convergence, is the convergence with respect to the topology, which is generated by the subbase of this form. So nu of F here, I'm using this notation. Nu of measure evaluated the function is integral of F with respect to the measure nu. So this is equal to the integral of F. Say x. Yes. So if you integrate F with respect to nu, then it should be in G, and so this is nu set of nu's that satisfy the condition. So this condition is defined by decided by F and G. So F has to be in this set of this space. So functions that are supported on this part. for some R, and G is just open set in R. So basically, this is defined in terms of the integral value of the measures. So very similar to weak convergence, but we are only considering f's that are that. So we exclude x that is support that has non-zero value in this part. So what this means is that we say that mu n converges to mu in this space if the integrated value converges to the integrated value of the integration with respect to the limit measure for all f in this space. So very similar to weak convergence, except that the class, it's not all bounded continuous functions. It's bounded continuous and supported on some set of this form. So because of this similarity, you would expect that there should be portmanteau theorem, and it is in this case. Again, this is from the probability survey paper by Linscoe, Roy, and Resnick. And again, very similar to the weak convergence version. You have, so the convergence in M is same as convergence in M. So here, this is convergence in M. Instead of all F, we have, if we add extra condition that we only check uniformly continuous functions, then it still is same as M convergence. And here, the supremum is bounded by bounded from above by the closed set. Infimum is bounded from below by the open set. And so this is probably what's different from what looks different from the regular weak convergence, because in regular weak convergence, it's like this. So only one of this is enough, right? But here we need both of these. Why? Because in standard weak convergence, G's are just the complement of F. The open sets are the complement of the closed sets. But here, if we take the complement of F that is bounded from C, the complement may not be bounded away from C. So you need separate conditions for both upper and lower bounds. And this is pretty much the same as this. So basically, if you have zero boundary mass, then it doesn't have to be lim sum and limit. It's actually exact limit. And then these two are relations to these two have to do with the relations with regular weak convergence. So you can characterize M convergence in terms of the weak convergence on so these are restrictions of so it should be, I think it should be R here as well. So these are restrictions of mu n and mu in this space. So now you can talk about the regular weak convergence on this space, and so you can characterize M convergence in terms of okay. So this is a regular version of M convergence, but what we need is uniform version. And a natural way to define the uniform version is so recall that the definition of M convergence was this converges to this, so these converge to this value. So integrations converge to integration of with respect to the limit measure. And of course, this can be written in this way. So if we consider a uniform version, then of course you have to you need parameterized sequence of parameterized measures, and we say that this parameterized sequence converges to this parameterized limit measure if the supremum of these integrated values, the difference in the integrated values, converges to 0 over whatever index set you have. So, very natural definition of uniform convergence. But do we have a nice portmanteau theorem? It turns out that we don't. So we do have new portmanteau theorem, but it's a little bit messy. So first, you need some sequential compactness of the limit measures. So in other words, given any sequence of parameters, if you can find a subsequence and a limit point such that this sequence of measures converge to this in M. So in other words, these parameterized family of limit measures or a sequentially compact set in terms of M topology in space M. So under this condition, we do have some form of portmanteau theorem. So we have, so that the definition of M convergence simply this thing. It's the same as the same thing with extra condition that it's uniformly continuous. So this is, yeah.
So the only the limit needs to be tight.
Right. So
That's
we
right.
do, these ones
That is the limit.
these ones don't matter. Right. Only this tightness compactness condition is about the limit measures.
Chang-Han, you don't assume that this parameter space is compact.
Which also
The
yeah,
capital
data,
set.
so right. We don't assume that, but so in the end, when we actually specialize to our context, will be considered it having compact parameters that actually corresponds to having compact measures, set of measures. So yeah, it will appear that way, but in principle, it doesn't have to be. All right. So
And sorry, again, like just to try to understand some of the context, like M convergence is a kind of like a modification extension of V convergence. So uniform M convergence. Is there in the literature a uniform version of V convergence?
so we didn't find so that yeah, I as far as I know okay. All right. So the uniform, like you don't need to check this convergence for all continuous functions. It's enough to check uniform functions. The third condition is this is what is going to be useful. So if you take the supremum over this, then the lim sup should be bounded by 0, and lim inf should be bounded from below by 0. If you take the infimum, so the consequence of this, implication of this, is this. So you take the lim sup of the supremum, then it should be bounded by the supremum. You take the lim inf of the infimum, then it should be bounded by the infimum as well. So you may ask whether these are the same or not. Obviously they are not, because here actually for fixed data this has to converge to this, but here only supremum should converge to this. It's enough. So you can have something, some easy but strange example. Pretty easy to come up with. So this is strictly weaker condition than these three. These three are all equivalent. Another thing is that here we have epsilon. This is also impossible to get rid of. So if you change this to just F and G without its epsilon, then this is too strong. It's stronger than the other conditions, so not equivalent. All right, so in other words, this is a little bit ugly, but this is really actually what it is. And it turns out that this is now this looks very familiar. This is what we needed. So so why is this useful? So this is what we want eventually, and this is what we can easily verify. In particular, the H here. So H with K large, let's say K largest jumps and uniform jump times. That is the skeleton that corresponds to the step functions with K jumps. So basically, that defines the macro behavior of SGD with ideal SGD, and the fluctuations from the small perturbations, you can bound it. So they don't contribute in the large deviations. So that's how we obtain the large deviations, and also the that's how we obtain the large deviation. Once we have large deviations, then we also have the asymptotic atom, which translates to this main theorem that I started with. This theorem. And now if you look at this, if you stare at this, then the scaled exit time is exponential, and you know exactly where it's going to jump to. So this should remind something, right? So the exponential holding time and the embedded Markov chain's transition kernel completely characterizes Markov jump processes, continuous time Markov processes with discrete space theory. So this actually completely characterizes the limit process in that way. So the transition is defined by this exit location, and exit times are exponentially distributed if you do the right scaling. So here, the largest scale, in other words, the widest attraction field is associated with the largest scale. The other local minima is associated with something asymptotically smaller exit time. So in the limit, they will just disappear, and you're only left with the exit times associated with the widest local minima. So that's why the limit process is a Markov jump process with with only the widest local minima. So let me finish with discussing this asymptotic atom in slightly more detail. So so this condition becomes pretty clear. This must be something that's like this is what you get really from the large deviations, sample path large deviations. This also because you need one jump to deviate from the gradient flow. So nominally it should follow gradient flow, and therefore you should hit atom. So this may not be as clear as the other ones, but so let me try to explain it. So remember that if you have something like this, then you will be attracted to the local minimum. So if the asymptotic atom is this, so that you cannot enter this part, and the I epsilon is slightly smaller than the attraction field, then it means that you should be here, and before it hits enters the asymptotic atom, you should jump again somewhere, but it cannot exit, and then you will be attracted again, and so forth. So the smallest number of jumps required here, it is the one that you get by waiting until the last moment and make as much jump as possible, waiting as much as you can, then make jump, and then wait again. So what this means is that this probability of this kind of path becomes smaller. The rate of this the rate at which this probability decays becomes smaller if you make the time horizon long enough. So if you pick this t long enough, then you can make this number of jumps required number of jumps arbitrarily large. So that's how you make this equal to 0 by choosing t infinity, choosing large t. So no matter what epsilon is chosen, you first fix it. You make t large. You make this required number of jumps large, so that this A is asymptotically irrelevant. And these things will be the same, because what's going to happen here is that you're going to be waiting, and then there will be just one jump, or whatever number of jumps. Or if you're starting from here, you will be waiting, and then you will make, let's say, 2 jumps to get out of it. So these will be not affected by choosing large t. This you can make it small. You can make it 0, and this is obviously pretty much always have to be equal to 1. So indeed, once you have large deviations, the sample path large deviations, these all come out as a result. All right, so let me finish with commenting one thing. So what we have done is very sharp characterization of the global dynamics of SGD. And it's about nominal behavior, how it behaves. But the way we have obtained this is through the exit time analysis, in turn from the rare event analysis. So the point I'd like to make here is that rare event analysis is not just about rare events. It can also characterize the nominal behavior. All right, thank you.
I have a question. You more or less explained how you complete the proof once you establish some complicated limit, right? How do you even go about that? I mean, these exit
Oh,
analysis.
you mean from here to the exponents, or from LD?
So from here to LDP, I understand you have all these generalized M convergence and all these things, but how do you even control this probability? This well?
So you mean how do we establish this?
Like the standard tools work, or is there some even
So these are
problem?
actually so these conditions can be established once you have large deviations. But
And how do you establish those standard deviations?
from here to large deviations. Okay.
Yes.
So so the point here is that if you so H here is what I've shown in here. So this is like if you decide the size and the time, then H is a mapping that maps those size and time to also a starting point to this particular path. So this is exactly same situation as the step functions with jump sizes and jump times. So this finite dimensional object determines the whole path. So and remember that those finite dimensional so here what dominates everything else is first k largest jumps. So those largest jumps will be will have very specific representation as the inverse pseudo inverse of the Levy measure scaled by n and evaluated at a gamma distribution, gamma random variable. So the sum of first k exponential random variables. So you have very good control of those random variables that live in the Euclidean space. So LDP of this thing, so the skeleton process comes from that, and then the challenge is to show that skeleton. So the actual SGD will be that plus small fluctuations that are so the smaller jump sizes. So there is so you can actually prove that those are bounded. Those are basically negligible compared to the first k largest one. So that and that was actually also the case in the same practically the same approach in the Levy process case or so the philosophy is the same. Take k largest, but of course here execution is a bit different because now you have handle solution of
Yes, that's what I was going to ask. So this sigma doesn't, I would imagine, complicate story. I mean, or the proof much more. Not do that.
Well, not very much in this. So I'm not sure how much it will simplify without with constant sigma, but maybe Shin you remember that it's better. Like if sigma is constant, is it going to be much easier?